Doppler effect. I'll be explaining this concept in 3 videos. The first video consisting of the first and the second case of Doppler effect, the second video of the third case of Doppler effect, and the third video on a very simple method in order to solve numericals that involve the Doppler effect. So what is the Doppler effect? The apparent change in the frequency of sound caused by the relative motion of either the sound or the source or the listener or both is called as the Doppler effect. In more simpler words, if we have a source which is emitting sound waves of actual frequency, then whatever the listener is hearing is apparent frequency, which is not the real frequency of the sound waves. This phenomenon is called as Doppler effect. There are some common terms which you need to understand in order to understand the Doppler effect. Besides that, you need to understand that whenever we talk about the source, we always talk about the person or the car and the sound waves that are being emitted by that person or that car or the horn that that person is carrying. So, the first thing is that whenever the source is moving, not only the wavelength of sound waves they change, but also the velocity of source it also changes. However, when the listener is moving, only and only the velocity of that listener and the velocity of those sound waves they change. Number 2 is that for our convenience, we have denoted the velocity of that source as a and the velocity of sound waves as v. But for the velocity of listener, we have b. The source, it always moves with the movement of sound waves. However, the listener, it always moves and changes its speed. And number 4 is that the source, it is emitting sound waves of frequency, which is called as the actual frequency, denoted by f. However, the listener is hearing sound waves of frequency, which is called as the apparent frequency, denoted by f dash. There are a total of 3 cases for the change in frequency, that is for the Doppler effect. The first 2 cases will be discussed in this video. Number 1, when the source is moving and the listener is at rest. And number 2, when the listener is moving and the source is at rest. The third case is when both the source and listener are moving. This will be discussed in the next video. Case number 1, when the listener moves and the source is at rest. The first part, when the listener moves towards the source and the source is at rest. Whenever the listener is moving, the velocity of that listener and the velocity of sound waves are also changing. In more simple words, when the sound waves are traveling towards the listener and the listener is traveling towards those sound waves, so whatever the speed of sound will be, it will be a combined effect of v and b. Therefore, the new speed of sound, that is v plus b. Since known by the simple formula, v is equals to f lambda, so f will be equals to v upon lambda. V has changed and that has resulted into v plus b. However, since the wavelength is not changing, since source is not moving, so we're just going to put in more simpler terms v upon f. So we have the last formula, that is f dash equals bracket v plus b upon v bracket close into f. Since the numerator is greater and thereby f dash, it is greater as compared to f. In more simpler terms, if I have a source and if I'm moving towards that source, so gradually as I move on, I will notice that the loudness or the frequency of that sound waves, they will increase. Case number 1, part 2, when the listener moves away from the source, but the source is at rest. Everything here is the same except for the fact that if the sound waves are moving towards the listener and the listener is moving away from the sound waves, so whatever the speed of sound that will be observed, it will be v minus the factor of b. Thereby, f dash will be equals to v minus b upon lambda. And putting the value of lambda as discussed earlier, so we have the most formula, the general formula, that is f dash equals to bracket v minus b upon v bracket close into f. Since here the denominator is greater as compared to the numerator, which has a subtraction sign, and thereby the apparent frequency is less as compared to the actual frequency. In more simpler terms, whenever we have a source which is at rest, and if I'm moving away from the source, so as I move on, I will notice that the loudness of sound, it will also decrease, that is the frequency of sound. Case number 2, part 1. When the source moves towards the listener, but the listener is at rest. The first thing to note here is that whenever the source is moving, the wavelength of the sound waves they are changing. In order to explain how the wavelength has changed, if we have the source, we can take it as one single point, whatever could be the source. It could be a person or car, whatever, a horn, etc. So if I've taken this source as a rectangle, and if I take this point 1 as the beginning of that source from where the sound waves are being emitted. So that point, after some time, capital T, it moves from this point to this point. At this instant, it has traveled a distance of AT. Now, how do you get this distance? Since we know by physics formula that S is equals to VT. And since I have taken for convenience the velocity of source as A, so replacing V by A, we have AT. Moving on, after some time, capital T, the sound waves, they will also move. If for convenience, I have taken only and only one sound wave, which has a lambda wavelength, and thereby this basically, if it has point 1 and point 2, so after some time, capital T, this point 1, it will move to the point 2, that is 1 dash, and the point 2, it will move to another point called as 2 dash. So it has traveled a total distance of vt since the velocity of these sound waves are for taken for convenience as v. Now, what is wavelength? Wavelength is the distance between two consecutive compressions, rarefactions, crest or trough or whatever. For simple convenience, we can say it is the distance between two waves. So, when the source it moves from this point to this point after some time capital T, not only the source moves, but also it starts to emit wavelengths of sound. So this new sound wave, which is going to be generated, it will have a distance of lambda from that point to the point where the sound wave that was basically traveled after some time capital T from point 1 to point 1 dash. So this will be a distance of lambda. And from diagram, we can see that if I subtract Vt by At, I can get lambda. Therefore, by mathematics formula, we have lambda is equals to Vt minus At. Taking T as common, so we have V minus A. So, in order to calculate the apparent frequency, since when the source is moving, we have a change in wavelength, that is T bracket V minus A. F is equals to V upon lambda. Since the listener is not moving, so V is not changing. The lambda that has changed, that is T V minus A. The reciprocal of time period equals F, and thereby we have, putting the value of F here, we have apparent frequency equals bracket V upon V minus A, bracket close, into F. Since the numerator is greater as compared to the denominator, so apparent frequency it is greater as compared to the actual frequency. In more simpler terms, if I am standing and if the source is moving towards me, so gradually with time I will notice that the loudness or the frequency of those sound waves appearing to me, they will increase. Case number 2, part B. When the source moves away from the listener and the listener is at rest. If we take the source to be producing sound waves from the back of that source, because we are discussing the listener and we want to discuss only those sound waves which are traveling towards the listener. So, if from point 1 it travels through some distance AT to another point, after some time capital T, so the sound waves they also move. If the initial points were 1 and 2, so that one point it has moved towards 2 and therefore it becomes 1 dash and 2 dash. Thereby the sound waves after traveling through some distance Vt in a time interval delta t, it has reached this point. And so to find the apparent frequency, we have the same concept. F is equals to V upon lambda. Here the lambda, that is the wavelength, we have changed it because the source is moving. So T, V plus A. We've already discussed that the reciprocal of time period is equals to frequency. Therefore, V upon V plus A bracket into F will be the apparent frequency. Since the denominator is greater as compared to the numerator, so the apparent frequency will be less as compared to the actual frequency. That is, in more simpler terms, if I am a listener and if the source is moving away from me, So obviously, gradually as time increases, I will notice that the loudness of sound will also decrease. That's it for today. Thank you for watching. Do check out my other videos and do press the bell icon to get my latest updates on my next video of Doppler effect.